Imagine that tomorrow night you look up at the moon and notice something strange. At first, nothing seems wrong. The moon is still there, hanging above the Earth exactly where you expect it to be, glowing softly against the dark sky, with the familiar patterns of bright and dark regions spread across its surface. And for a moment, you might even feel the same quiet comfort that humans have felt for thousands of years whenever they have looked up and seen it watching over the night. Then you notice a second object. It is not bright, it does not shine, it does not reflect sunlight, it does not look like a planet, a star, or anything you have ever seen in the sky. It is simply a small, perfectly dark region sitting between the Earth and the moon. And the strange thing is that the darkness itself seems to be moving, not quickly and not dramatically, but slowly enough that you can almost convince yourself that your eyes are playing tricks on you. Then the moon moves slightly, not across the sky, in its orbit. A tiny change, almost impossible to notice without instruments, but large enough for astronomers to become deeply concerned. Because something has entered the space between Earth and the moon, and whatever it is, it has gravity, a lot of gravity. It is a black hole. Now, before we imagine the Earth being swallowed into darkness, there is something very important we need to understand. Because the first thing most people imagine when they hear the words black hole is probably wrong. A black hole is not a cosmic vacuum cleaner that automatically pulls in everything around it. If the Sun was somehow replaced by a black hole with exactly the same mass, the Earth would continue orbiting almost exactly as it does now. The sky would become very different because we would lose sunlight and heat, but the Earth's orbit would not suddenly collapse inward simply because the object had become a black hole. From far enough away, gravity mostly cares about mass. It does not care whether that mass is made of ordinary matter, compressed into a star, or hidden behind an event horizon. And that means the real question is not simply what happens if a black hole comes near Earth. The real question is much more interesting. How much does the black hole weigh? How close does it come? How fast is it moving? And most importantly, what happens when its gravity reaches into the delicate space between Earth and the moon? Because the distance between Earth and the moon feels enormous when you stand on Earth. The moon is about 384,000 kilometers away on average, which is so far that you could place dozens of Earths between them if you somehow lined them up. But on the scale of gravity, this distance is not very large at all. The moon is held to the Earth by gravity. The oceans rise and fall because of the moon's gravity. The Earth itself moves slightly because of the moon. And the moon does not simply sit in the sky. It is constantly falling around us. It is moving forward through space, while Earth's gravity continuously pulls it inward, creating the curved path we call an orbit. This balance has been happening for billions of years. The Earth pulls on the moon pulls on the Earth, the Sun pulls on both of them, and the entire system is moving through the solar system, while the solar system itself moves through the Milky Way. It is an enormous gravitational dance that looks simple from the surface of Earth, only because we have been watching it from one tiny location. Now imagine placing another massive object directly into that dance. Not near Jupiter, not somewhere beyond Neptune, not millions of kilometers away, right between Earth and the moon. At first, the black hole might not look impressive at all. If it had the mass of Earth, its event horizon would be incredibly small compared with the size of the Earth. The entire mass of our planet would be compressed into an object with a radius of only about 9 millimeters if it were turned into a non-rotating black hole. That means something with the mass of Earth could have an event horizon roughly the size of a small marble. This is one of the strangest things about black holes. The object itself can be tiny, while its gravity reaches enormously far. So from Earth, you would not see a giant black sphere stretching across the sky. You would see almost nothing. And that is what would make the situation so terrifying. The black hole could be smaller than a marble, but if it had the mass of Earth, the moon would know it was there. Earth would know it was there. Every satellite would know it was there. And the orbit of the moon would begin to change. At first, the change might be small. The moon would not instantly fly away. it would not instantly crash into Earth. Instead, the gravitational system would begin to deform. Think about a perfectly balanced sheet of fabric with two heavy objects sitting on it. Now place a third object between them. The shape of the fabric changes. The paths that were stable before are no longer the same. Space does not behave exactly like a fabric, but the analogy helps us imagine what is happening. Earth is pulling on the Moon is pulling on Earth, and now the black hole is pulling on both. The important part is that the black hole is not pulling equally on every part of Earth. The side of Earth facing the black hole is slightly closer to it than the far side. That difference matters. It is called a tidal effect, and tides are where this story begins to become much more interesting, because gravity itself is not the only danger. The difference in gravity across an object can be even more important. You can see this effect with the Moon. The side of Earth facing the Moon feels slightly stronger lunar gravity than the side facing away from the Moon. That difference stretches the Earth very slightly. It moves the oceans. It creates tides. It contributes to the slow breaking of Earth's rotation. It changes the orbit of the Moon. The Moon is already pulling on our planet every single day. Now imagine adding another massive object into the same neighborhood. If the black hole were far enough away, we might simply detect its presence through tiny changes in the Moon's orbit. Astronomers would notice that something was wrong long before ordinary people saw anything strange in the sky. The Moon would begin arriving at slightly different positions than predicted. Satellites would drift from their expected paths. Spacecraft traveling around Earth would require unexpected corrections. The International Space Station, if it still existed in this scenario, would experience changes in its orbit. The oceans would begin responding to the changing gravitational field, and every measurement of the Earth-Moon system would begin telling us the same thing. Something massive had entered the neighborhood. But suppose we were watching from the surface. Suppose the black hole was passing through the space between Earth and the Moon. At first, you might look at the Moon and see nothing unusual. Then, over hours or days, depending on the speed of the black hole, the Moon's orbit would begin to shift. And this is where the story becomes uncomfortable, because the Moon's orbit is not simply a circle, it is an ellipse. The Moon's distance from Earth changes, its speed changes, its position relative to the Sun changes, and its orbit is already being influenced by the gravity of the Sun, Earth, and other bodies. The black hole would arrive as a new gravitational player in a system that has been stable for an extremely long time. Imagine taking a perfectly tuned clock and placing a magnet next to its moving parts. The clock does not necessarily explode, it simply stops behaving the way you expect. That is what could happen to the Earth-Moon system. And the first major mystery would be this: would the black hole steal the Moon? Because it is possible, not inevitable, not even necessarily likely for every trajectory, but possible. If the black hole passed close enough to the Moon at the right speed and from the right direction, its gravity could alter the Moon's velocity so strongly that the Moon would leave its familiar orbit around Earth. The Moon could enter a new orbit around the black hole. It could be thrown into a wider orbit. It could be pushed into a highly stretched elliptical path. Or it could even be sent away from both objects. The exact result would depend on the black hole's mass, its speed, and the geometry of the encounter. This is important because there is no single answer to the question, what would a black hole do? Gravity is not a simple on-off switch. Distance matters, mass matters, velocity matters, and timing matters. A black hole passing between Earth and the Moon at extremely high speed could produce a very different outcome from a black hole moving slowly through the same region. The slower it moves, the longer Earth and the Moon would remain inside its changing gravitational influence. The faster it moves, the more sudden the disturbance would be. And this gives us several possible versions of the same nightmare. In one version, the black hole passes through the system so quickly that Earth and Moon are disturbed but remain gravitationally bound. In another version, the Moon is captured or thrown into a completely different orbit. In another, Earth's orbit around the Sun is altered. And in the most extreme cases, the gravitational encounter could become destructive. But there is something else that makes this scenario so strange. The black hole would not necessarily look black, at least not in the way you might imagine. A black hole by itself does not shine, but if it passes through a region containing gas, dust, asteroids, or other material, that material can become extremely hot as it falls toward the black hole. Matter can form an accretion disk around it. That disk can glow intensely. So the most dangerous black hole might not be the one you can see. A black hole moving through an almost empty region of space could be nearly invisible. We might discover it only because stars behind it appear distorted. Light from distant objects can bend around massive objects. This is called gravitational lensing. A black hole can therefore reveal itself by changing the appearance of the universe behind it. Imagine looking at the moon and seeing a small dark object near it. Behind that object are distant stars. As the black hole moves, those stars might appear to shift. Some could brighten, some could appear stretched. Some could produce strange rings of light. And astronomers would understand almost immediately that something extraordinary was happening. But ordinary people might not. They might simply notice that the moon looks wrong. And that is one of the most disturbing things about space. The most important events can begin as changes too small for human eyes to notice. The universe does not always announce danger with an explosion. Sometimes it begins with an orbit changing by a few centimeters. Sometimes it begins with a star moving slightly from where it should be. Sometimes it begins with a clock ticking differently. And sometimes, something enormous can move through space while remaining almost completely invisible. Now let us imagine that our black hole has approximately the mass of Earth, and that it is approaching the Moon's orbit. At a distance of hundreds of thousands of kilometers, Earth's gravity still dominates the Moon's local environment in a broad sense, but the black hole is adding a new force. As it gets closer, its influence increases rapidly. If you cut the distance in half, the gravitational force becomes 4 times stronger. If you reduce the distance by 10 times, the force becomes 100 times stronger. This inverse square relationship is one of the simplest and most important rules in gravitational physics, and it means that the final part of the encounter can change much faster than the beginning. For days, perhaps, almost nothing obvious might happen. Then the black hole gets closer, and suddenly the numbers start moving quickly. The Moon's orbital velocity changes, Earth's center of mass shifts, the oceans respond, satellites drift. The shape of Earth's orbit begins to change, and the Moon begins to fall into a new gravitational story. Now imagine standing on Earth during this period. The sky might still look peaceful. There could be stars. There could be clouds. There could be city lights. There could be people driving home from work, children sleeping, airplanes crossing the night sky, and millions of ordinary lives continuing without knowing that the gravitational structure of their world is changing. That contrast is what makes this scenario so powerful. The apocalypse would not necessarily begin with fire. It could begin with mathematics, a number on an astronomer's screen, a tiny deviation in the Moon's position, a spacecraft drifting several meters farther than expected. And then, slowly, the evidence becomes impossible to ignore. Something is pulling on the Moon, something that should not be there, something that cannot be seen. Eventually, if the black hole came close enough, we would begin to notice changes in the tides. The Moon already controls much of the regular rhythm of Earth's ocean tides, although the Sun also plays a major role. If the black hole were massive enough and close enough, its own tidal force could become significant. The oceans would respond to the changing gravitational field. But this does not mean that giant walls of water would automatically rise into the sky. That popular image is too simple. The real response would depend on the black hole's trajectory, mass, distance, and how quickly the gravitational field changed. Some regions could experience unusually strong tides. Coastal waters could move in strange ways. Ocean currents could change. The timing of high and low tides could become unpredictable. And if the disturbance were strong enough, coastal regions could face catastrophic flooding. But even this would only be the beginning. because the Earth is not a solid rock floating alone in space. The planet itself would respond. The crust would experience tidal stresses. The atmosphere would be affected indirectly through changes in the surface and ocean system. Earth's rotation could be altered slightly, and the Moon's changing orbit could create consequences that continue long after the black hole has disappeared. This is an important idea. The black hole does not have to stay. It only has to pass close enough. A gravitational encounter can permanently change an orbit. Imagine throwing a ball past another ball. If the second ball has enough mass, its gravity can bend the first ball's path. If the encounter is arranged correctly, the first ball leaves moving in a different direction and with a different speed. Now replace those balls with planets and moons. The same basic physics applies. The difference is that the consequences are enormous. The Moon could leave the Earth with more orbital energy, or it could lose energy. Its orbit could become larger or smaller. Its eccentricity could increase. Its orbital plane could change. And depending on how violent the encounter was, the Moon might eventually collide with Earth, escape Earth entirely, or settle into a strange new orbit. But there is another possibility that sounds almost impossible. The black hole could capture the Moon. If the encounter conditions allowed it, the Moon could become a companion of the black hole instead of the Earth. Imagine looking into the night sky after the encounter and seeing no familiar Moon. The tides would begin changing. The nights would become darker. The ancient object that had shaped calendars, myths, religions, stories, and human history would no longer occupy its familiar place. But the black hole would still be there, invisible, silent, moving through the darkness. And now the Earth would have to continue without the Moon. That alone would create a cascade of long-term changes. The Moon helps stabilize Earth's axial tilt. Without it, Earth's tilt could become more variable over extremely long periods. That would affect the climate. But these changes would not necessarily happen overnight. This is another place where real science is more interesting than disaster movies. Some consequences would happen within hours. Others would take years. Others would take thousands or millions of years. A good way to think about the event is as a disturbance moving through time. The black hole arrives. Gravity changes, orbits change. Then the black hole leaves. But the new orbits remain. The universe remembers gravitational encounters through motion. A planet does not need to keep the object nearby to remember that it was there. Its velocity has changed. Its orbit has changed. Its future has changed. And that means the Earth could continue experiencing consequences long after the black hole had passed beyond the Moon. Now there is an even bigger question. Could the black hole actually hit Earth? If it were an Earth-mass black hole, the event horizon would be extremely small. So even though its gravitational influence could be enormous, physically colliding with it would require an incredibly precise trajectory. It would not sweep across Earth like a giant dark planet. It would be more like an invisible gravitational projectile. And if it passed directly through Earth, the situation would become far more extreme. The black hole would move through the planet while pulling matter toward it. The surrounding material would be violently disturbed. Earth's interior would experience enormous gravitational stresses. Matter near the black hole's path could be captured, heated, compressed, and accelerated. But the black hole would not necessarily swallow the entire Earth instantly. That is another popular misconception. A small black hole with the mass of Earth would not simply open its mouth and consume a planet in one bite. The rate at which matter could be captured depends on many factors, including the black hole's size, velocity, and the behavior of matter around it. Still, a direct encounter would be catastrophic. The Earth would not remain the same. But our scenario is more interesting because the black hole does not hit Earth. It passes between Earth and the Moon. That means we are watching a gravitational near-miss, and near-misses can be more complicated than direct collisions. A collision gives you one obvious result. A near-miss gives you a new orbit. And new orbits can survive for billions of years. Suppose the black hole passes between Earth and the Moon and continues outward. At the moment it reaches its closest approach, its gravitational pull on Earth and Moon becomes strongest. Then it begins to move away. the force weakens. The oceans begin responding to the changing field. The moon continues along its new path. Earth continues orbiting the sun, and the black hole disappears into the distance. For a few hours or days, perhaps, humanity might remain obsessed with tracking it. Every telescope would turn toward it. Every space agency would calculate its trajectory. Every observatory capable of detecting gravitational effects would be watching. Scientists would compare measurements from different countries. Satellites would be used to measure the changing gravitational field. The moon would become one of the most important objects in astronomy because its orbit would act like a giant natural detector. We could measure how much its motion had changed, and from that, we could begin reconstructing the mass and trajectory of the invisible object. In a strange way, the moon would become our witness. It would tell us where the black hole had been, but there would be something else happening in the background. The Earth itself would have moved. Not because the black hole physically pushed it like a hand pushing a ball. Gravity does not work that way. Instead, the Earth and black hole would pull on each other. The center of mass of the system would shift. Earth's velocity could change. And because Earth orbits the Sun, even a small change in its velocity can alter its long-term orbit. This is where the consequences become planetary rather than lunar. The black hole does not need to capture Earth. It only needs to change Earth's motion enough to create a new orbit around the Sun. Perhaps the difference would be small. Perhaps Earth would move into a slightly more elliptical orbit. Perhaps the change would be larger. And if the encounter were extreme enough, Earth's orbit could move significantly farther from or closer to the Sun. That would change the amount of sunlight reaching the planet. A small orbital change might have limited immediate effects. A larger one could affect climate over long periods. Move Earth closer to the Sun, and temperatures rise. Move Earth farther away, and temperatures fall. But again, the exact outcome depends on the black hole's mass and trajectory. This is why a serious version of this thought experiment cannot simply say, the black hole comes close and Earth is destroyed. The universe is more complicated, and that complexity is exactly what makes the story worth exploring. Because perhaps the black hole passes between Earth and Moon, and Earth survives. Perhaps the Moon survives too. Perhaps there are no immediate global fires. Perhaps the oceans do not fly into space. Perhaps the atmosphere remains. Perhaps people wake up the next morning and the world is still there. But the moon is different, and that could be enough. Imagine scientists announcing that the moon is now moving away from Earth on a completely new trajectory. For generations, people have looked at the moon and assumed it would always be there. But now its orbit has changed. Perhaps it is slowly escaping. Perhaps it will remain bound, but much farther away. Perhaps its orbit has become highly elliptical, bringing it unusually close to Earth at some times and carrying it far away at others. The sky itself would become unfamiliar. The moon would rise at different times. Its phases would change at different rates. Its apparent size would change more dramatically. The tides would follow a new rhythm, and human beings would have to relearn the night sky. This is one of the most fascinating parts of orbital mechanics. The sky is not a painting. Everything is moving. The moon is moving. Earth is moving. The sun is moving. The planets are moving. The stars are moving. Even the Milky Way is moving. What feels permanent is often only something that changes slowly enough for human life to mistake it for permanence. The moon has been with Earth for billions of years, but billions of years are not the same as forever. A black hole passing through the Earth-Moon system would remind us of that. Now let us slow the story down. The black hole has passed. The immediate danger is over. The object continues outward. Earth is still here. The moon is still here. But the gravitational system has been rewritten. And now the real question begins. What happens next? Suppose the moon remains bound to Earth but in a new orbit. The tides change. The length of the lunar month changes. The relationship between the moon and Earth's rotation changes. Over long periods, this could affect the way the Earth spins. The moon has always acted like a gravitational brake on Earth's rotation. As tidal friction transfers energy from Earth's rotation into the moon's orbital motion, Earth's spin gradually slows. If the moon's distance changes dramatically, that process changes too. The future of Earth's day could therefore be different. And this is one of those consequences that would be almost impossible to notice at first. You would not wake up the morning after the encounter and suddenly have a 48-hour day. Instead, tiny changes would accumulate, milliseconds, seconds. Then, over enormous periods, larger differences. The black hole would be long gone. Human civilizations might rise and disappear. Continents would move. Oceans would change. Species would evolve. And the altered moon would continue influencing the planet. That is the strange legacy of gravity. It can reach across enormous distances and leave effects that survive long after the original event. Now imagine the black hole itself continuing through the solar system. If it passed between Earth and Moon, it would not simply stop there. It would continue moving. Depending on its velocity and trajectory, it could pass near another planet, perhaps Mars, perhaps Venus, perhaps an asteroid belt region. Each encounter could alter another orbit. And if the black hole were massive enough, it could become a gravitational troublemaker moving through the solar system. The planets would not necessarily be swallowed. In fact, direct collisions would be extremely unlikely. Space is enormous, but their orbits could change. A planet could gain energy, another could lose energy. A small body could be thrown into a completely different orbit. An asteroid could be ejected from the solar system. Another could be sent inward toward the sun. The black hole could essentially move through the solar system like an invisible gravitational disturbance. And every planet it passed would become part of the story. This is where the idea of a black hole becomes less like a monster and more like a mathematical object. It does not need to chase anything. It does not need to attack anything. It simply follows the rules of gravity. And those rules are enough. Now return to Earth. Imagine standing outside at night after the black hole has passed. The moon is still visible, but it is no longer where it used to be. Perhaps it looks smaller because its orbit has moved outward. Perhaps it appears larger because its orbit has become more elliptical. Perhaps it is temporarily moving away from us. The stars look the same. The sky feels familiar. But something has changed. And you know that the thing that changed is not just the moon. It is the entire future of the Earth-Moon system. This is the part of the story where we need to ask a question that sounds simple, but is actually enormous. What if the black hole were not Earth mass? Because the mass of the black hole changes everything. Imagine a black hole with the mass of the moon. Its event horizon would be even smaller. Its gravitational influence would be weaker than an Earth mass black hole at the same distance. It could still disturb the moon and Earth if it passed close enough, but the results would be different. Now imagine a black hole with the mass of the Sun. Its event horizon would be only a few kilometers across, yet its gravitational influence would be enormous. If a solar mass black hole passed between Earth and Moon, the Earth-Moon system would be in serious danger. The Moon could be violently displaced. Earth's orbit around the Sun could change dramatically. The tides could become extreme, and the gravitational environment around our planet would become completely unfamiliar. But even then, the black hole would not magically suck everything into itself. Its mass would determine the gravitational field. Its distance would determine how strongly that field affects us, and its speed would determine how long the disturbance lasts. This is why the phrase, "black hole passed between Earth and the Moon," hides a huge amount of physics inside a single sentence. It sounds like one event. It is actually a family of possible events. A tiny, primordial black hole with the right mass could behave differently from a stellar mass black hole. A rapidly moving black hole could behave differently from one moving slowly. A black hole passing close to the Moon could produce a different outcome from one passing exactly halfway between Earth and Moon. And a black hole approaching along the Moon's direction of motion could create a different gravitational exchange from one approaching perpendicular to the orbital plane. Every detail matters, but there is one thing we can say with confidence. The Moon would not simply ignore it. Earth would not simply ignore it. The solar system would notice, and if the object were massive enough, humanity would have no way to stop it. There would be no missile powerful enough, no spacecraft fast enough, no shield that could block gravity, no machine that could push the black hole away. The only thing we could do would be to watch, measure, calculate, and wait. And that might be the most frightening part. Human beings are used to solving problems by interacting with them. If something is falling, we can catch it. If something is approaching, we can move. If something is dangerous, we can build a barrier. But gravity does not care about barriers. A black hole does not need to touch Earth to affect Earth. It could remain hundreds of thousands of kilometers away and still reshape the orbit of our moon. The only defense would be distance, and in this scenario, the distance is disappearing. Imagine the final hours before closest approach. Astronomers have calculated the trajectory. Every telescope is watching. The black hole itself remains invisible except through its effects. The moon's position is changing. Satellites are being moved or shut down. Space agencies are running simulations constantly. Scientists are comparing possible outcomes. The public is watching the sky. And somewhere between Earth and the moon, something with enormous mass is moving through the darkness. It does not make a sound. There is no shockwave traveling through space. There is no visible wall of destruction. There is only gravity. And as the object gets closer, the gravitational field becomes stronger. The moon begins to move. Earth begins to move. The oceans respond, and for a moment, the familiar geometry of our world becomes something completely different. Then the black hole reaches its closest point. This is the moment when the entire system is most unstable. The black hole has passed through the space between two worlds that have been gravitationally connected for billions of years. Earth is pulling one way, the moon is being pulled another. The black hole is pulling on both. And then, slowly, the black hole begins to leave. The danger starts moving away, but the consequences remain. That is where our story becomes less about destruction and more about memory. Because after the black hole disappears into the darkness, Earth will continue. The sun will rise. People will go outside. Birds will fly. Cars will move. Cities will remain. The oceans will continue to move against the shores. But the moon will follow a new path. And the Earth will follow a new path too. The solar system will have been changed by an object that nobody could see. Perhaps the black hole will never return. Perhaps it will travel between the stars for millions of years. Perhaps it will eventually pass near another planetary system. And somewhere far away, another world could one day experience the same strange event. A dark object appearing in the gravitational equations. A planet's orbit beginning to change. A moon moving slightly away from its predicted path. Scientists wondering what could possibly be causing it. And then the realization. Something invisible is passing through. This is one reason black holes are so fascinating. They force us to separate what we can see from what actually exists. For most of human history, we understood the universe primarily through light. We looked at the sun. We looked at the moon. We watched stars. We mapped planets. But gravity tells us that the universe contains things that may not shine at all. Objects can exist without producing visible light. Their presence can be revealed only by the way they move everything around them. A black hole is perhaps the most extreme example. It is not defined by what we see. It is defined by what gravity allows. And if one ever passed between Earth and the moon would become our detector. The oceans would become detectors. Satellites would become detectors. Earth itself would become a detector. Every orbit would tell us that something enormous had passed nearby. And perhaps the most beautiful part is that the same laws that allow us to predict the danger also allow us to understand it. The equations do not panic. They do not care whether the object is beautiful or terrifying. They simply describe motion. Mass creates gravity. Gravity changes motion. Motion changes orbits. And orbits create the structure of planetary systems. For billions of years, the Earth and Moon have followed those rules. And for billions of years, the system has been remarkably stable. Until, in our impossible scenario, a black hole arrives. At first, it is only a point in a calculation. Then it is a disturbance. Then it is a new gravitational force. Then it is a changing moon. Then it is a changing Earth. And finally, it is gone. But the universe is not reset. The new motion remains. The black hole has moved on, but Earth carries the consequences forward. And perhaps that is the deepest lesson hidden inside this strange thought experiment. Space looks empty. The distance between Earth and the Moon looks like nothing but darkness. But that darkness is not empty in the way we imagine. It is filled with fields, particles, radiation, gravity, and motion. The Moon is not simply hanging above us, it is falling. Earth is not sitting still, it is orbiting. The Sun is not stationary, it is moving through the galaxy. And the galaxy itself is moving through a universe that is constantly changing. Everything is connected through motion. Everything is responding to everything else. So when we imagine a black hole passing between Earth and the Moon, we are not really imagining a monster entering an empty space. We are imagining a new participant entering an already moving system, and the system responds. Perhaps the Moon survives. Perhaps Earth survives. Perhaps humanity survives. But the old orbit is gone. The old predictions are gone. And the night sky that once felt permanent has become a reminder that nothing in the universe is truly fixed. Even the Moon can be moved. Even the Earth can be redirected. And somewhere in the darkness, the black hole continues traveling. Silent, invisible, carrying the gravity of everything it contains into a future that may be millions or billions of years away. And if it never comes back, the Earth will eventually stop thinking about it. Civilizations will forget. Records will disappear. Languages will change. The people who watched the black hole pass will become part of history. The telescopes that tracked it will stop working. The satellites that measured its gravity will fall silent. But the Moon will still remember. Not in a conscious way, of course. It will remember through its orbit, through the path it takes around Earth, through the tides it creates, through the way it affects the rotation of the planet. And Earth will remember too, through its altered path around the Sun, through the motion of its oceans, through the slow turning of its atmosphere, through changes that may last long after the original event has become almost impossible to imagine. That is the strange permanence of gravity. You do not have to leave a mark on the surface of a planet to change its future. Sometimes all you have to do is pass nearby. And in a universe filled with billions of stars, trillions of planets, and objects moving through enormous distances, there is no law saying that such encounters cannot happen. The universe is quiet, but it is never still. And somewhere beyond the Moon, beyond the Earth, beyond the familiar planets, something may be moving through the darkness right now. We simply do not know what is there. Perhaps that is what makes the night sky so beautiful. When you look up, you are not looking at a finished picture. You are looking at a system in motion, a universe where planets can wander, stars can explode, galaxies can collide, and black holes can travel silently through the dark. And if one ever crossed the space between Earth and the Moon, the event would not just be a story about a black hole. It would be a story about how fragile the familiar arrangement of our world really is. The Moon seems permanent because human lives are short. The Earth seems stable because civilizations are short. The solar system seems fixed because even 1,000 years is almost nothing compared with the time it takes planets to change their paths. But underneath that apparent stability, gravity is always working, always pulling, always moving, always reshaping. And if an invisible object with enough mass entered the space between our planet and its moon, we would finally see just how powerful that quiet force really is. Not because the black hole would roar, not because it would shine, not because it would announce itself, but because everything around it would begin to move. And that might be the first clue that something impossible had entered our sky. The Moon would move, the Earth would move, the oceans would move, the satellites would move, the planets would move. And for a brief moment in cosmic history, the entire future of our world would depend on one simple question: where is the black hole going next? The strange thing about a black hole passing between Earth and the Moon is that the most dangerous moment might not look dangerous at all. There may be no giant explosion in the sky, no sudden flash of light, and no enormous wave racing across the Earth, because a black hole does not work like a cosmic vacuum cleaner that suddenly sucks everything around it into darkness. Instead, the danger would begin quietly. The Moon might still look almost normal. The stars might still be visible. The oceans might still be moving. People might still be driving home, making dinner, checking their phones, watching television, or looking up at the night sky without realizing that something has entered one of the most important gravitational spaces around our planet. And that is what makes this situation so frightening, because if a black hole passed directly between Earth and the Moon, the first thing it would attack would not necessarily be the Earth itself. It would attack the balance. For billions of years, the Earth and Moon have been moving through space in a very specific gravitational relationship. And although that relationship feels completely stable to us, it is actually a carefully maintained dance in which every object is constantly pulling on every other object. The Earth pulls on the Moon pulls on the Earth, the Sun pulls on both. And every planet in the solar system adds a tiny gravitational influence to the system as well. Normally, these effects are so predictable that scientists can calculate where the Moon will be years, decades, and even centuries into the future. But now imagine placing a black hole between the Earth and the Moon. Suddenly, there is a new gravitational source sitting in the middle of the dance. And unlike the Moon, which is relatively small and familiar, the black hole could be incredibly dense. Even if the black hole were only a few times more massive than the Sun, its physical size could be surprisingly tiny compared with the distance between Earth and the Moon. That is one of the first ideas that makes black holes so difficult to understand. Their gravity can be enormous without the object itself taking up a huge amount of space. A black hole with the mass of the Sun would have an event horizon only a few kilometers across. That means you could have an object with the mass of an entire star sitting inside a region smaller than a city. And if that object crossed the space between Earth and the Moon, the problem would not be that its event horizon suddenly reached across the distance and swallowed the Earth. The problem would be gravity. Gravity does not care whether you can see the object. It does not care whether the object is glowing. It does not care whether the object has a surface. If something has mass, it bends space-time around it. And if that mass suddenly becomes part of the Earth-Moon system, every orbit around it has to respond. The Moon would feel it first. Not because the Moon would necessarily fall directly into the black hole, but because its path through space would begin to change. Imagine throwing a ball around a person who is standing in the middle of a field. If the person stays where they are, you can predict the ball's path. Now imagine another person suddenly walks into the field and starts pulling the ball sideways with a rope. The ball does not need to hit the second person to have its path changed. The same basic idea applies here, except the rope is gravity and the field is space-time. The Moon would be pulled toward the black hole. Earth would be pulled toward it too, but they would not necessarily be pulled equally. And that difference is extremely important, because when two parts of an object experience slightly different gravitational forces, the object can be stretched, squeezed, twisted, or even torn apart. This is called a tidal effect. We already see tidal effects from the Moon itself. The Moon's gravity pulls slightly more strongly on the side of Earth that faces the Moon, and slightly less strongly on the side facing away from it. That difference helps create Earth's tides. The black hole would do the same thing, but if it came close enough, the effect could become much stronger. The ocean would begin responding, the atmosphere would respond, the solid Earth would respond, and the Moon would respond. The entire Earth-Moon system would begin to deform under the changing gravitational field. At first, these changes could be small enough that nobody notices. The tides might become strange. Coastal waters might rise higher than expected. Some tides might arrive at unusual times. The Moon's position in the sky might begin to drift from the prediction, and astronomers would notice something very strange. the moon would not be where the calculations said it should be. That would be the first major warning. Because scientists know the moon's orbit extremely well, they can measure its distance from Earth with extraordinary precision. So if an unknown object were passing through the Earth-Moon system, they would not need to see the black hole directly to know something was wrong. They could simply watch the moon. If its orbit suddenly changed in a way that could not be explained by known objects, scientists would begin looking for the missing cause. And then they would have one of the most terrifying discoveries in human history. Something massive was passing through our neighborhood. Something invisible. Something that could not be seen directly. And something that was close enough to change the orbit of the moon. But even then, Earth would not necessarily be doomed. This is where the story becomes more interesting, because the outcome depends almost completely on one thing: mass. The phrase, "a black hole between Earth and the moon," sounds like one specific event, but black holes can have wildly different masses. A black hole could have the mass of a small mountain. It could have the mass of the Earth. It could have several times the mass of the Sun. It could have millions or billions of times the mass of the Sun. And each version would create a completely different story. A tiny black hole passing between Earth and the moon might create a strange gravitational disturbance and then continue moving away. A black hole with the mass of Earth could seriously disturb the moon's orbit. A black hole with the mass of the Sun could completely destroy the current Earth-Moon configuration. And a supermassive black hole would make the entire situation almost impossible to survive. So let's imagine something in the middle. Not a monster with millions of solar masses, not a microscopic object. Instead, imagine a black hole with roughly the mass of the Sun. It has somehow entered the solar system and is moving toward the space between Earth and the moon. The first thing that would happen is not what movies usually show. There would be no giant black circle suddenly appearing in the sky. A black hole does not look like a black ball floating against the stars. From a distance, it could be almost impossible to notice. If there were no glowing gas around it, you might see absolutely nothing. But its gravity would still be there, and as it approached, the paths of nearby objects would begin to change. The moon would be the obvious victim, but Earth would not sit still either. Earth would begin accelerating toward the black hole. The moon would also accelerate toward it, and because the black hole would be between them, the geometry of the entire system would become extremely strange. For a short period of time, the Earth and Moon could both be moving toward the same gravitational source, but they would not simply fall straight into it. Everything in space is already moving. The Earth is orbiting the Sun at roughly 30 kilometers per second. The Moon is orbiting Earth at roughly 1 kilometer per second. The black hole would have its own velocity through the solar system. So what happens would depend on the direction and speed of all three objects. This is one reason real orbital mechanics can be so complicated. You cannot simply say, the black hole is closer, so everything falls into it. Objects can swing around massive bodies. They can gain energy. They can lose energy. Their direction can change dramatically. A spacecraft does this intentionally when it uses a planet's gravity to alter its trajectory. The same physics that allows a spacecraft to use Jupiter as a gravitational slingshot would apply to the black hole. The difference is that a black hole could be far more massive, and the Earth-Moon system was never designed for this. There is another strange possibility. The black hole might pass between Earth and the Moon so quickly that the event is over before the Earth has time to respond dramatically. The gravitational disturbance would still happen, but it could be brief. The black hole could bend the Moon's orbit, disturb Earth's motion, and then continue on its way into the solar system. In that case, Earth might survive, but the Moon could be left on a completely different orbit. It might move farther away, it might move closer, it might become highly elliptical, or, depending on the exact encounter, it could potentially be ejected from Earth's orbit altogether. Imagine looking at the Moon one night and seeing it exactly where it has always been. Then, over the following days and weeks, its position begins to change. Not because the Moon has suddenly developed a new engine, not because the Sun has changed, but because an invisible object has rewritten its orbit. The Moon could begin taking a much longer path around Earth. Its distance could increase dramatically. and as it moves farther away, the tides would weaken. The familiar rhythm of Earth's oceans would begin to change. But if the moon moved closer, the opposite would happen. The tides could become much stronger. And if the moon came close enough, tidal forces could become catastrophic. The oceans would not simply rise like a giant wall. Instead, Earth's entire tidal system would become much more powerful and complicated. Coastal regions could experience extreme flooding. Ocean currents could change. The rotation of Earth could be affected. And the solid planet itself would experience stronger tidal deformation. Earth is not perfectly rigid. It bends, it stretches, it moves. We normally do not notice because the forces involved are tiny, but a nearby massive object could make those movements much larger. The ground beneath your feet could rise and fall by measurable amounts. The planet could experience intense seismic activity. And this is where the phrase "black hole passing between Earth and Moon" stops being a simple space story and becomes a story about the stability of an entire planetary system. Because the black hole would not just affect the Moon, it would affect Earth. And the Earth would affect the black hole. The black hole would gain energy from the interaction. The Earth would change velocity. The Moon would change velocity. And the Sun would eventually feel the consequences too. This does not mean the black hole would pull the entire solar system apart like a vacuum cleaner. The solar system is huge. The distances between the planets are enormous. But gravitational disturbances can travel through the system in the form of changed orbital motion. If Earth's orbit around the Sun changed even slightly, that could alter the long-term climate of the planet. A small change in Earth's orbital distance can affect the amount of sunlight Earth receives. A large enough change could make the planet colder or hotter over long periods. But the black hole would not necessarily push Earth directly toward the Sun. It could send Earth into a new orbit. Earth could move into a slightly larger orbit, or a slightly smaller one. Or in a more extreme encounter, its orbit could become highly stretched. Then the planet would travel much farther from the Sun during one part of its year, and much closer during another. That would create enormous changes in climate. But we have still not reached the most visually spectacular part. Because if the black hole passed close enough to the Moon, something extraordinary could happen. The Moon could become distorted by gravitational lensing. Light from distant stars passing near the black hole would bend around it. The night sky could begin to look wrong. Stars might appear displaced. Some could appear brighter. Some could appear to form strange arcs. And in the right geometry, the black hole could produce an Einstein ring. Imagine looking into the night sky and seeing a dark center surrounded by a perfect ring of distorted starlight. That would be one of the most beautiful and terrifying sights humanity had ever seen. And the strange thing is that the black hole itself would still be invisible. You would not be looking at the black hole. You would be looking at what the black hole does to the light around it. The sky would become a gravitational mirror. Stars behind the black hole could appear in completely different positions. A single star could even appear as multiple images. The closer the alignment, the stronger the distortion. And if the black hole passed directly between Earth and a distant star, the star's light could bend around the black hole and reach us along paths that normally would not exist. For a brief period, the universe would look like it had been bent. But while people were watching the sky, something much more important would be happening below. The Moon's orbit would be changing, and if the black hole were massive enough, the Moon could become trapped in a new orbit around it. This is one of the possibilities that sounds like science fiction, but comes directly from orbital mechanics. The Moon does not belong to Earth in an absolute sense. It is gravitationally bound to Earth. That means if another massive object passes close enough and moves in the right way, the Moon's orbital energy can change. It could potentially become bound to the black hole instead. Now imagine that. The Moon, which has been Earth's companion for billions of years, suddenly becomes a companion of something else. From Earth, the Moon could begin moving across the sky in a completely unfamiliar way. Its distance could change, its speed could change, its phase cycle could change, the tides would change, and eventually, the Moon could disappear from Earth's sky altogether. Not because it exploded, not because it was swallowed, but because gravity stole it. And there is another possibility that is even more disturbing. The black hole could pass close enough to the Earth itself. If that happened, the difference in gravity between one side of Earth and the other would become enormous. The side facing the black hole would feel a much stronger pull than the side facing away. That difference would stretch the planet. This is the same basic process responsible for tidal forces, but pushed to an extreme. Near a sufficiently massive compact object, these forces can become so strong that matter is stretched dramatically. Scientists sometimes call this process spaghettification. The name sounds almost funny. The reality is not. But there is an important detail. You do not automatically get spaghettified just because a black hole is nearby. It depends on the black hole's mass and your distance from it. A small black hole can have extremely strong tidal forces close to its event horizon. A supermassive black hole can actually have weaker tidal forces at its event horizon because the horizon is so much larger. That means the phrase black hole by itself does not tell us how dangerous it is. Mass tells us, distance tells us, velocity tells us, and the path of the encounter tells us. So let's make the black hole more massive. Imagine it has 10 times the mass of the Sun. Now the situation becomes much worse. A black hole like this would have an event horizon only tens of kilometers across, but its gravitational influence would extend enormously far beyond that. If it came between Earth and the Moon, Earth would be moving through an intense gravitational field. The Moon's orbit could be completely destroyed. Earth's orbit around the Sun could change, and the black hole itself could become temporarily part of the solar system. If its speed were low enough, the Sun might capture it. Then the solar system would have a new massive member, a black hole orbiting the Sun. That sounds impossible because we imagine the solar system as a finished structure, but there is nothing in the laws of physics saying that a black hole cannot orbit a star. If a black hole passed through the solar system and lost enough orbital energy through gravitational interactions, it could remain gravitationally bound to the Sun. Then Earth would not have survived a single passing event. It would now be living in a solar system with a black hole. The black hole could orbit the Sun for millions of years. Its gravity would slowly disturb the planets. The exact outcome would depend on its orbit. If it stayed far away, the disturbance could be relatively small. If it passed through the inner solar system repeatedly, the effects could become severe. And every time it came near Earth, the planet's orbit could change again. This is where the story becomes less like a disaster movie and more like a cosmic game of billiards. The planets are moving balls. The Sun is the largest ball. The black hole is another extremely massive ball. And every gravitational encounter changes the future path of everything involved. One close encounter can be enough to send an object into deep space. Another can send it toward the Sun. Another can capture it into a new orbit. And sometimes, an object can exchange energy with another body and escape entirely. If Earth received enough energy during the encounter, it could be pushed into a larger solar orbit. If it lost energy, it could move inward. If the disturbance were extreme, Earth could potentially be ejected from the solar system, and that would be one of the strangest endings imaginable. The Earth would still exist. The oceans would still exist. The mountains would still exist. The atmosphere might still exist. Human civilization could still be standing. But the planet would no longer orbit the Sun. The sky would slowly change. The Sun would appear smaller and smaller. Temperatures would begin to fall. The oceans would eventually freeze from the surface downward. The atmosphere would begin to collapse. And Earth would become a wandering planet, moving through the darkness between stars. All because an invisible object passed through the space between Earth and the Moon. But there is another question. Could we see the black hole before it arrived? The answer is maybe, and this is where the story becomes surprisingly realistic. A black hole does not have to be visible to be detected. Astronomers could look for its gravitational effects. Stars behind it could appear distorted. Planets could shift slightly in their orbits. Spacecraft could experience unexpected changes in trajectory. Light could be gravitationally bent, and if the black hole were feeding on gas, it could become extremely bright. Gas falling toward a black hole does not simply disappear quietly. It can form an accretion disk. Material spirals inward. Friction and compression heat the material to enormous temperatures. The disk can shine across the electromagnetic spectrum. In some cases, a black hole can become one of the brightest objects in the universe. But suppose this black hole were completely isolated. No gas, no dust, no nearby star, nothing to feed on. Then it could remain almost completely dark. We might only know it was there because stars started moving strangely. That possibility is especially unsettling. Imagine astronomers tracking a star thousands of light years away. They know exactly where the star should be. Then its position changes. Not much, just a tiny amount. At first it looks like measurement error. Then another star does the same thing. Then another. Eventually astronomers realize that the light from distant stars is being bent by something massive that they cannot see. They calculate its position. They calculate its mass. They calculate its speed. And then they discover that its path leads toward Earth. At that point, there would be no way to stop it. There is no weapon large enough. There is no engine powerful enough. There is no shield that can block gravity. Humanity would have only one option: watch and wait. But even then, there would be an important question. How much warning would we have? That depends on the speed of the black hole and how far away it was when we detected it. If it were moving through the solar system at hundreds of kilometers per second, it could cross astronomical distances surprisingly quickly. But astronomers could potentially detect its effects long before it reached the Earth-Moon system. The first signs might appear in the orbits of distant objects. The outer planets could show tiny gravitational changes. Asteroids could be disturbed. Comets could change direction. And the farther away the black hole was, the more time scientists would have to notice the disturbance. The solar system would begin to reveal the intruder before the intruder ever reached Earth. But suppose nobody detected it. Suppose the black hole came from a direction where there were few useful observations. Suppose it was dark, isolated, and moving quickly. Eventually, it would enter the inner solar system. The planets would begin responding. And by the time it reached the distance of Earth, the gravitational effects would be impossible to ignore. The Moon would no longer behave normally. Earth's orbit would begin to shift. Satellites would begin moving in strange ways. GPS systems would become less accurate because their orbital calculations would suddenly be wrong. Communication satellites could drift. Weather satellites could move out of position. The International Space Station, if it still existed, would have to deal with changing orbital conditions. And spacecraft across the solar system would begin reporting anomalies. Scientists would know. The black hole had arrived. Now imagine standing outside at night. You look up. The Moon is there. But something is wrong. It is moving slightly differently. The stars near a certain region of the sky appear distorted. A bright star seems to have shifted position. Then another. The Moon's predicted location and its actual location are no longer the same. And somewhere between Earth and the Moon, an object with the mass of a star is passing silently through the darkness. You cannot hear it. You cannot see it. You cannot touch it. But the entire sky is responding to it. That is the real horror of a black hole. It does not need to announce itself. The universe announces it for you. And now the most important question becomes unavoidable. Would the Earth survive? For some black holes, yes. For others, absolutely not. If the black hole were small enough and moving fast enough, the encounter could be more like a cosmic bullet passing through the solar system. It could disturb the Moon, disturb Earth, and continue into interstellar space. Earth could remain intact. The Moon could remain in orbit. Civilization could survive. But the solar system would never be exactly the same. The Moon might have a different orbit. Earth might have a slightly different orbit around the Sun. Some satellites might be lost. Some asteroids might be thrown onto new paths. And years later, astronomers might still be measuring the consequences. If the black hole were more massive, however, the damage would become much greater. And if it moved slowly enough to become captured by the sun, the danger would not end after one pass. The black hole would remain. It would continue orbiting, and every orbit would be another gravitational disturbance. The solar system would become unstable over time. Mercury could be affected first because it is close to the Sun, then Venus, then Earth, then Mars. The black hole would not need to hit any planet. It would only need to disturb the paths enough. That is the strange thing about orbital systems. You do not have to destroy an object directly to destroy its future. You only have to change its velocity. A tiny change today can become a completely different orbit millions of years later. This is why scientists are so careful when studying gravitational encounters. The important thing is not simply where an object is now, it is where its motion takes it. And that means the black hole could create consequences that continue long after it has disappeared. Imagine that the black hole passes through the Earth-Moon system and then leaves. 10 minutes later, it is already far away. 1 day later, farther still. A year later, it may be billions of kilometers away. But Earth is still living with the new orbit. The Moon is still following its new path. The oceans are still responding. The satellites are still adjusting. And the solar system is still slowly reacting. The black hole could be gone, but its gravitational fingerprint would remain. This is similar to throwing a stone into a pond. The stone can disappear beneath the water in seconds, but the waves continue spreading. The difference is that in space, the waves are changes in motion and gravity rather than water. And there is one more possibility that makes the event even stranger. The black hole could pass so close to the Moon that it tears material from the Moon itself. The Moon is mostly rock. It is strong, but no material is infinitely strong. If tidal forces became extreme enough, the Moon could be pulled apart. Chunks of lunar rock could be thrown into new orbits. A ring of debris could form. Some pieces could fall toward Earth. Others could orbit the black hole. Some could escape completely. And the Moon could be transformed from a solid world into a stream of fragments. From Earth, the sky would become unbelievable. Instead of one moon, there could be thousands of bright pieces moving across the sky. Some could enter Earth's atmosphere. There could be meteor storms unlike anything humanity had ever seen. The night could become bright with burning debris. And while people watched the spectacle, the underlying cause would be invisible. The black hole itself would remain dark. This is one reason black holes are so powerful as a story. They create visible consequences without being visible themselves. You see the stars bend. You see the Moon move. You see the tides rise. You see the sky change. But the thing responsible is hidden. And hidden danger is often more frightening than visible danger. Still, there is something we need to remember. The Earth-Moon system is not a fragile glass ornament floating in space. It is an enormous gravitational system. The Moon is about 384,000 kilometers away. That sounds enormous, but on the scale of the solar system, it is actually very close. The Sun is roughly 150 million kilometers away. Jupiter is hundreds of millions of kilometers away. The nearest stars are trillions of kilometers away. So placing a black hole between Earth and the Moon would put an incredibly massive object extremely close to us. That alone would guarantee a major gravitational disturbance if the black hole had significant mass. But it would not automatically mean that the Earth gets swallowed. This is one of the biggest myths about black holes. A black hole does not pull everything from an unlimited distance. If the Sun were magically replaced by a black hole with exactly the same mass, Earth would continue orbiting almost exactly as before. The sky would become dark because there would be no sunlight, but Earth's orbit would not suddenly collapse. The reason is simple. At a given distance, gravity depends mainly on mass. The fact that the object is a black hole matters enormously when you get very close. But from far away, a black hole can gravitationally behave like any other object with the same mass. So if a black hole with the mass of Earth passed between Earth and Moon, the Earth would not be instantly sucked inside. It would simply experience the gravity of another Earth mass object. the moon would respond. The Earth would respond. The exact result would depend on their relative velocities and distances. And this leads to an interesting thought. A black hole could pass between Earth and Moon without ever coming close enough to its own event horizon. In other words, the black hole could be incredibly dangerous without ever touching anything. Its gravity would do all the work. You would see everything you have seen before, but slowly, almost invisibly, the positions would begin to change. The moon would drift from its predicted path. The tides would change. Satellites would move. Astronomers would stare at their instruments, and somewhere between Earth and the moon, a region of space would be bending light around an object that no human eye could directly see. If the black hole were small enough, perhaps Earth would survive. If it were massive enough, perhaps the moon would be lost. If it were extremely massive or moved slowly enough, perhaps the entire solar system would be rearranged. There is no single answer because the universe does not respond to dramatic names. It responds to numbers, mass, distance, velocity, direction, time. Those 5 things would decide our fate. And that is perhaps the most important lesson hidden inside this impossible scenario. The universe does not need an explosion to destroy a world. Sometimes all it needs is a change in motion. A tiny change in velocity can move a planet into a different orbit. A different orbit can change its temperature. A changed temperature can change its atmosphere. A changed atmosphere can change its oceans. And eventually, a single gravitational encounter can influence the future of an entire civilization. So imagine the black hole finally passing the moon. For a few minutes, perhaps the sky is filled with strange gravitational distortions. For a few hours, the moon's path changes. For days, scientists calculate. For months, satellites adjust. For years, the oceans settle into new rhythms. For centuries, humanity adapts. And for millions of years, Earth continues traveling through space on a path that is no longer the same path it had before. The black hole is gone, but the Earth remembers, not with a scar on its surface, not with a crater, not with a mark that can be seen from space. It remembers through its orbit, through the moon, through the tides, through the position of the planets, through the shape of the solar system itself. And somewhere far beyond the orbit of Neptune, the black hole continues moving through the darkness. Perhaps it will never return. Perhaps it will pass through another star system. Perhaps it will wander between stars for billions of years. Perhaps one day it will encounter another planet, with another moon, and another civilization, wondering what is happening to their sky. And if they were watching from that distant world, they might see exactly what we would see. The stars bending, the moon moving, the universe becoming strange, and an invisible object passing silently through the darkness. Because that is what black holes do. They do not need to shine. They do not need to roar. They do not need to announce themselves. They simply move through the universe, carrying gravity with them. And if one ever passed between Earth and the moon, the question would not be whether we could see it. The question would be how much of the world around us could remain unchanged after it was gone. For a planet that has spent billions of years following the same gravitational dance, even a brief encounter could be enough to change the next billion years. And that is why, in this impossible scenario, the most dangerous moment would not necessarily be when the black hole was closest. It might be the moment after it had already passed. Because that is when we would finally realize that the old Earth-Moon system was gone, and something new had taken its place. Something that would continue moving through space long after everyone alive today had disappeared. The black hole would keep going. The Earth would keep going. The moon, if it survived, would keep going. The sun would keep going. And the universe would continue expanding around all of them. No explosion, no final sound, just gravity, just motion, and an invisible traveler moving through the dark. Good night.